We're going to move into chapter 3 and talk about matter and energy. This is what our lab is about this week on Wednesday, so this will give you a good start to be able to do the pre-lab stuff, and it'll make the lab make more sense. But hopefully all of this will make more sense after we actually do the lab. So first thing we're going to do is just define some terms. Classification of matter, not super exciting, but matter is anything, any material, any kind of stuff, and we can fit it into some different categories, which becomes important when we start looking at the chemical reactions and the things that matter does. So we need to separate it into these categories. We're first just going to separate this big category, of matter into two main. Now I got nothing. Into two main categories. Let's see. Maybe if we do this. Nope. Okay. Main categories. We're going to have pure substances and mixtures. So that seems pretty straightforward. You got pure substances, you got mixtures. Either something's pure or it's not. But then there's this question of like, well, what does it mean to be pure? What does it mean for something to actually be a pure substance? So we're going to define that a little bit farther. And we're going to say there are two types of pure substances. Elements and compounds. Elements are probably the easiest one to think about. Those are the elements. They're made. That means that every atom in a pure element is the same type of atom. And in a couple chapters, we'll talk about atomic structure, but it means every atom is the same. So that's a pure element. So you're talking about things like everything that you would find on the periodic table. So that could be gold or silver or hydrogen gas or oxygen gas, whatever, some stuff from the periodic table. Pure elements can have like a single symbol, like AU for gold. They can also kind of look like a chemical formula, like oxygen is O2 because there's two oxygen atoms, but it's still just oxygen, so we still call that just a pure element, pure oxygen. Compounds is where we start to get a little bit trickier, because compounds are still pure substances, but they're made of multiple elements.
Like water.
Yeah, like water. So now you've got multiple elements, but they're chemically bound together, and that's what makes it pure. But think about water. Water's chemical formula is H2O, which means it's made of hydrogen and oxygen. It's a pure substance because the hydrogen and oxygen are chemically bound together. Does anybody know what you get if you break apart the hydrogen and oxygen from water? Well, you get something, but you get two gases. You get hydrogen gas, you get oxygen gas. That's not the same as water. So that's what this is talking about, that when you chemically connect those things, and we'll talk about what that means in the next 3 chapters, you make a different substance, and that's still considered a pure compound. So something like sodium chloride, NaCl, table salt. That's another example of a pure substance. It's not a mixture, but it's made of multiple elements. And this is probably the trickiest one on the whole table, even the stuff we haven't done yet. This is the one that people get mixed up with the most, because it's a little tricky to think about, okay, it's a pure substance, but it's made of multiple elements. So this would be multiple elements that are chemically bound together, that can only be broken apart through a chemical reaction that changes what it is. So something like sucrose, which is table sugar. Again, it's a chemical compound. It's got a lot of elements in it, in that molecule, but it's still a single pure substance. So there's our pure substances. You've got elements and you've got compounds. Compounds, you'll always be able to write like a chemical formula. You'll always be able to write that formula of those elements connected together. The other side of the table here, the mixtures, you can't. It's always this and this and this together. There's no nice, neat chemical formula for that. So mixtures can also be separated into two parts. We have homogeneous mixtures and heterogeneous mixtures. All right. And this has to do with how closely the particles in the mixtures are mixed together. So a mixture in general means you have more than one substance, more than one element or compound mixed together. So the pure substances, or I'm sorry, the homogeneous mixture, we're going to say it has a uniform composition throughout, which just means that the particles in a homogeneous mixture are so small and in such close contact that it looks like one thing. So that's what we mean uniform composition throughout. It looks like one thing, or it acts like one thing. So for example, coffee. Coffee's a mixture. It's got a lot of different compounds in it. It's got, I don't know, what's some stuff that's in coffee? Sugar. Coffee beans. You should take those out. Try drinking it without the beans in it. It's better. But yeah, like the stuff from the coffee beans, right? Yeah. So it's like caffeine, flavors, color molecules. Water is it's the main part of coffee. So there's a lot of different things there. But it's clearly uniform throughout. Like when you look at a cup of coffee, you don't see the water on one side and the caffeine on the other side or something like that. You can't pick out little pockets of sugar. It's all the same throughout the whole thing. So that would be a homogeneous mixture. You can also have, homogeneous mixtures are another word for that is sometimes a solution. Things mixed together, that's like what we use in lab a lot. Something like salt dissolved in water, salt water. Salt water is a pretty simple mixture between salt or sodium chloride and water, but again, it looks uniform throughout. If it's dissolved, you can't find the salt and the water in separate places. So it's a homogeneous mixture. You can have homogeneous mixtures of not just liquids and solids too, like air is a homogeneous mixture. What's in air? Yeah. Nitrogen, oxygen, hydrogen, a little bit. Carbon dioxide and water vapor are the major parts of air. There are small amounts of other gases too in air. But so that's a homogeneous mixture. That air is all mixed together, and or those gases are all mixed together. You could have solid homogeneous mixtures, like has anybody ever heard of the different carats of gold that you can get, like 14 karat gold and whatever? Does anybody know what pure gold is? Yeah, but how many carats is it? Close. It's 24. 24 carats is pure gold. So why don't we usually have 24 karat jewelry? It's expensive, yeah, but there's another reason too. I think somebody said it. Yeah, it's really soft. Gold is really soft. You can kind of bend it. And so if you made a ring or something out of 24 karat gold, it would be easily smushed or cracked or scratched. So instead, it's alloyed with other metals like silver, maybe nickel or zinc, depending on copper, depending on the formulation, and that's how we get 14 karat gold or 10 karat gold, which is now stronger. But again, you don't see like silver parts in your 14 karat gold. It just looks all golds because it's a homogeneous mixture. It's all the same. So then the last one is the heterogeneous mixture, where it's not a uniform composition throughout. We would just say not uniform or separated, however you want to think about that. So can anybody think of an example of a heterogeneous mixture? Thanks. Can anybody think of a heterogeneous mixture? What? Heterogeneous, what? Orange juice, yeah. Orange juice with the pulp. How many people here are with pulp? Prefer the with pulp? A few. Without pulp? Everybody else without pulp? So we could put that in there. Orange juice with pulp. Anything that would separate if you let it sit long enough, we would consider a heterogeneous mixture. Any others? Apple cider, sure, because it's got kind of like a sediment to it, right? Are we only thinking of delicious juices? Trying to make me hungry?
Not that you can drink that, but
What? Yeah, it could be. So like that kind of gets to a good point that in a lot of these, it's not necessarily really clear. Like if you said sugar and water, one person might think of that as, oh, sugar is dissolved in water and it's homogeneous. But somebody else might think of that as you put the sugar in water and it falls to the bottom, so it's heterogeneous. So you really have to be specific about what you're talking about with these. Is it actually dissolved or is it just sitting there? Maybe instead of that, we would say, just to be clear, we could say something like sand in water. That would definitely be heterogeneous because it would never dissolve because it's sand. Yeah, I think you. Yeah, granite's a good example, sure. Anybody know what granite looks like? It's kind of rock, and you can see like black parts and different color parts in it. So that would be heterogeneous mixture of minerals. Do you want to? What? Oh, ramen, sure, yeah. A lot of foods that we could see different parts of. What do you like to put in your ramen? What?
A lot of noodles.
A lot of noodles? Yeah. Egg? Yeah. Sounds good. Should we let's just end class and go get some food. I'm hungry. All right, so you get the idea of this separation here. So one of the things that you're going to get to do in your homework to practice is to classify things in one category or another. So let me give you one. Chocolate chip ice cream. Where would that fit in here?
It's a mixture.
It's a mixture. What type of mixture? Heterogeneous? Yeah, because you can see the chocolate chips, right? They're separate. What about the methane in natural gas? It's a pure substance. Is it an element or a compound? Methane? Anybody know? Anybody know the chemical formula for methane? It's CH4. So what does that make it? It's got to be a compound. It's got carbon and hydrogen. What about natural gas itself? The stuff that comes out of here that lights your burner. Any idea? It is not pure.
It's a mixture.
It's a mixture because methane's part of it. But yeah, it's a homogeneous mixture because I don't know why I just turned that on. That's not safe. Methane is in there. But there's also ethane. There's some other gases because it's refined from oil. So it's not just one substance. That makes it a homogeneous mixture. Okay, good. So it sounds like you kind of got that idea. All right, let's move on. Talk a little bit about. So one of the things we want to talk about is how do you separate these things out, both like how do you know which one's which, but how do you actually physically separate the components? Because that can be another way of determining that. So another way that we could differentiate these is we could say, okay, elements are pure, but compounds can be separated, but they can only be separated by chemical reactions. Whereas these mixtures, both homogeneous and heterogeneous, can be separated by physical means, which means that we can separate them without actually changing the constituent parts. All right, so let's look at an example here. Take salt water, because that's a simple one. Salt water is a homogeneous mixture of salt and water, salt dissolved in the water. How could you separate the salt from the water?
Heat it up so the water evaporates.
Yeah, you could heat it up so the water evaporates. Because let's say it's so dissolved that you couldn't even filter it because it's like, you know, it just looks totally clear. So it's a solution. So you could heat it up. You don't even have to heat it up. You could just wait. And eventually the water would evaporate and the salt would be left behind. So that would be a way of separating that mixture. But you haven't changed the identity of either of those components. You still have salt and you still have water. They're just separated. So that's an example of a physical separation. A physical separation leaves everything intact. It's just no longer together. That's how you separate a mixture. But a compound can only be separated by a chemical reaction where you change the identity of what you have. You actually change it into something else. So the way that it would be great if we could just look at the elements and see, oh, the elements have stayed together or they haven't or whatever. It's not usually that simple. We do some chemistry, we do some process, and then we see what happens. So what we have to do is think about what happens and whether or not that's caused by a physical or chemical change. So can you think about some chemical reactions that you've seen? We did one last week. What are some things that tend to happen in a chemical reaction? Some things that you experience, yeah. A change in color, yeah, that's a good example. So if you separate things in a mixture, it's probably not going to change color, right? Because you're not changing any of the constituent parts. That can be a little tricky because if you mix colors, then it can look like it's changing colors, right? But yeah, color changes is a good one.
Changes matter.
What?
Changes in matter.
How?
Like bubbles that make gas.
Okay, so like producing a gas or something like that. That can definitely signify a chemical reaction. Again, we have to be a little bit careful there because what about something like boiling water? Is that a chemical reaction? It's not. You still have water, but it's bubbling and creating a gas, right? So yeah, if it sort of spontaneously creates bubbles, that's probably a good example that you've got a chemical reaction. What else? Yeah, that's a big one, and that's one that we're going to look at in lab on Wednesday. Temperature changes, because if you just separate things, chances are there's not going to be energy difference associated with that. But if you're breaking chemical bonds or forming chemical bonds, that takes or releases energy. So when you do chemical reactions, things will often get hot or cold. And that's an example of that too. So the key is thinking about what's happening and physical, and whether or not there's a change to the identity of the components. All right, so here's some examples. Gasoline burns in air. Would you call that chemical or physical? Chemical. It is chemical. Why? How do you know?
When the gasoline burns in the air, it's creating heat.
Yeah, so that's one, is that you know that that's creating heat. Okay, so that's a sign. What's another sign that this is a chemical reaction? Any ideas?
Yes.
Yeah, the gasoline no longer is there. So it's not that you've just separated the different parts of it. It's that it no longer is there. It's turned into something else. It's become carbon dioxide and water. It's burned up, or carbon monoxide, whatever it's burned up into. It's burned up into some stuff. So it's no longer really there. So that's your other sign that it's chemical. All right, what about sugar dissolves in water, forms a solution? Is that chemical or physical? Why is that physical?
Because unlike the last one, it's still there, but it just kind of
Yeah.
changed form.
Yeah, so that's exactly right. The sugar dissolves in water. What are you left with? You're not left with some magical new thing. It's just sugar and water together in the same solution. Yeah. So that's a physical change. You've made a mixture. All right, we'll do another one. Iron rusts. So you got a car, got some exposed iron, starts to rust. What do you think? Is that chemical or physical? Why?
Because the iron itself is being changed.
Yeah. Yeah, does everybody see that? How that might work? That, iron is like shiny metal that is, you can bend it, you can dent it. And then iron oxide, which is rust, is very different. It's red, it's brittle, it cracks apart, all that stuff. So that's evidence that you've really changed it. And so that's a chemical. I had a car that rusted so bad there were giant holes in the doors. Cars don't seem to rust like that anymore, but they used to. You just get these giant, and we just like put big pieces of metal over them, just kind of riveted it to the door so that the wind wouldn't come in so much. My friend had one where the floor was rusted out. You couldn't put your feet down. Did you have that? You had to hold your feet up? Yeah. That's not safe. I'm glad cars don't do that anymore. All right, so we got chemical and physical changes. Feel pretty good about that. All right. That's one thing we're going to do on Wednesdays. We're going to do some chemical and physical changes, and you'll see what happens. All right, so let's look at temperature. Anybody know what temperature is? Like how we define it officially? What are you measuring when you measure the temperature? It's what? It's not a trick question. Do you have an idea? Yeah, it's measuring the movement of atoms and molecules, of molecular or atomic motion. A lot of people say heat. It's not actually a measure of heat. Heat is a change in temperature. Heat is something that causes a change in temperature. But the temperature itself is actually a measure of molecular motion, so molecules moving around. And I think the best way to talk about temperature is to look at this picture from the book. So I'm going to copy it in here so we can all look at it together. This is on page 65 if you have the latest edition. You want to look at it up at home, but you can just take a look at it up here with us for now. So here is some 3 thermometers in boiling water. And they all are measuring a different temperature scale. So one is in the Kelvin scale, one is in the Celsius scale, and one is in the Fahrenheit scale. What you can see here is the red, maybe you can see it, the red line is up to that top horizontal line. That's the temperature of boiling water. The temperature of boiling water is 100 degrees Celsius, it's 212 degrees Fahrenheit, 303 kelvins. We're pretty familiar with the Fahrenheit scale usually around here. We may or may not be familiar with the Celsius scale. That's the one we're always going to use in lab. That's what we used last week in lab. Probably not so familiar with the Kelvin scale. The Kelvin scale has these really, really high numbers. And does anybody know what it's for? Why it's useful? Yeah, the Kelvin is the only one that doesn't have negative numbers. So 0 Kelvin is the absolute bottom of the temperature scale, which is called absolute zero, and it's when molecules stop moving. And so you can't go any lower than that because temperature is a measure of molecular motion. Yeah?
So what is that useful? Who uses that the most?
Yeah, so it's useful for really, really cold things because, like, let's say you are dealing with liquid helium. Liquid helium is about 4 kelvins in temperature. So then you can talk about 4 kelvins instead of minus 269, which is what it would be in Celsius. So if you've got really cold temperatures, it makes sense to use kelvins. But more importantly, when you're doing calculations with temperature with other quantities also, when you're using temperature as a factor in some sort of a calculation, you often can't use negative numbers. Because think about all the other units we use. Meters, grams, liters, they don't have a negative side of that scale for all that stuff. So a Kelvin, you'll notice also here, the Kelvin doesn't have a degree symbol on it. It's actually a unit, just like grams and liters and things. So you actually say kelvins instead of degrees Kelvin or Kelvin degrees. So that means that you can use it, and it plays nice with these other units like meters and grams and things like that for calculations because it doesn't have negatives. The Celsius kind of throws it all off because of the negative numbers if you try to do these calculations. So anyway, that's why. We won't use that Kelvin scale much in this class really at all. We'll stick to the other two. It is important to go between the other two because most of the rest of the world uses the Celsius scale. So it's important to know what people are talking about. And the one thing I really like about this figure is it shows a few things. It shows you the difference between the two scales. Converting between Celsius and Fahrenheit isn't as simple as a conversion factor because the degrees are different sizes and they start in a different place. So like if you look at between the freezing point of water and the boiling point of water, that's 100 Celsius degrees between 0 and 100, but it's 180 Fahrenheit degrees, 32 to 212. So the degree size of a Fahrenheit degree is smaller than a Celsius degree size. But they also start in different places because the 0C is the freezing point of water and 0F is much colder than the freezing point of water. So to convert between those, you actually have to use a special equation and you plug the number in one side or the other. And we'll look at that in a minute, but you won't have to just be able to do that off the top of your head. I think the most important thing about the scale is these 3 landmarks that are listed by those lines, and you should know these. You should know I don't care about the Kelvin scale, but between Celsius and Fahrenheit, you should know the boiling point of water, you should know the freezing point of water, and you should know the normal body temperature. In Celsius and Fahrenheit, yeah. You know, if you're taking somebody's temperature and your thermometer is stuck on Celsius or you can't figure out how to switch it to Fahrenheit and it says 37, you can't be like, oh, I think you're frozen. Because it doesn't work that way. So you have a sense that that's right. Also, when we do talk about the conversions, it's really helpful if you can know if your conversion is in the right realm or not, or if it makes no sense. Yeah.
What is 336 in Celsius? Sound like 94, 92?
No, not quite. It's just under. It's like 90. Yeah, more like 96-ish, something like that. Yeah, because it's 180 Fahrenheit degrees per Celsius, so it's not quite 2 to 1. So it's less than 2 degrees less. Yeah. All right, so let's look at how to convert between those two scales. The Kelvin scale is actually pretty easy. We can just put this one up here. You just add 273 to the Celsius temperature. So the temperature in Kelvin is the temperature in Celsius, plus 273. So it's just added. The degrees are the same size, they just start in a different place. 0 degrees C is 273 kelvins. The other ones is where it gets a little bit tricky. So let's take a look at these two equations. If you want to go from Fahrenheit to Celsius, so you want to solve for the Celsius temperature, you take the Fahrenheit temperature, you subtract 32, and then you divide by 1.8. And you don't have to remember these equations. You'll be given them if you need them. To go the other way is the opposite, but you have to do a little algebra to get around there. So the solution there is the Fahrenheit temperature is going to be 1.8 times the Celsius temperature, and then plus 32. So this is relatively straightforward. You plug the number in to the equation and you solve it on a calculator. The only thing that's tricky is you have to be careful of the order of operations. In the Celsius one, when you're solving for Celsius, you have to make sure to subtract the 32 first. So if you want to put some parentheses there to remind yourself, you have to do that first. On modern graphing calculators, scientific calculators, if you just type like a number minus 32 and then divided by 1.8, all like in one string, it'll divide by 1.8 first, and then do the subtraction, and you'll end up with the wrong number. So you got to remember to do the subtraction first in that one. So let's try it with just the body temperature. So let's say we know body temperature is 98.6 degrees F. How do we convert that to Celsius? Well, we want to solve for Celsius, so we would say the Celsius temperature is 98.6 divided by 32 divided by 1.8. So if I do this on a, that's right, I got rid of my calculator. If I do this on a standard calculator like this, I want to go 98.6 minus 32. Make sure I hit enter first, and then divide by 1.8. Get 37. Does anybody have a graphing calculator out today? You have one? Can you type it in the wrong way and see what we get? If you don't mind. So don't use the parentheses and just do 98.6 minus 32 divided by 1.8. Without it, yeah. Just like type it in a line. What do you get? Okay, maybe it's figured it out. What do you need something?
Yeah.
Yeah. So maybe it figured it out, but if it doesn't come up, it would come out to about 80 if you do it wrong. And so that's where having these landmarks ideas comes in. So if you get something, you can always ask yourself, does this number actually make sense? Does it make sense that 98.6 degrees is 80 C? And you would say, no, that doesn't make sense. It should be around 37. And then you know you did something wrong and you could go fix it. All right. So questions about those temperature scales? You'll get a little practice doing this on Wednesday in lab. All right, so we talked about temperature, and I said temperature wasn't the same as heat. So let's talk about heat and energy. So heat is one way to transfer energy. What is the other way to transfer energy? Anybody know? Did you say ocean? Oh, motion. Yeah, work. It's called work. But yeah. So like if you move something over a distance, that's another way of transferring energy from yourself to whatever you're moving. But heat is a transfer of energy. So one thing loses energy, another thing gains energy, and that's considered a heat transfer. Anybody know what the units of energy usually are? There's several different ones. Does anybody know a unit of energy? Calories is one. We'll focus on that one for a second. Does anybody know the definition of a calorie? A calorie it takes 1 calorie of energy to raise 1 gram of water, 1 degree C. So you got a gram of water, which the density of water, remember, is 1 gram per milliliter. So that's this much water. So if you have that much water, and you raise its temperature from, let's say, 23 degrees to 24 degrees, you put in 1 calorie of energy. So that's how a calorie is defined. We'll come back to that later with this idea of specific heat. That's a calorie. Now, calories can be kind of a confusing unit because we also use calories in our food, right? Are those the same calories? They're not. Anybody know the difference? No, the calories in food are actually a different unit that has a capital C. And it's 1,000 of those calories we were just talking about. And it's extra confusing because C is one of those letters that looks the same capital or lowercase, so you could really be off by 1,000 by just making your letter too big or too small, which is dumb. Yeah?
So if you're like running on the treadmill and it's giving you the number of calories you're burning, is it
It's the big C calories.
Okay.
Yeah, because everywhere else in the world calls these what they should be called, which is kilocalories or kcals. And you'll even see that on most nutrition labels now. That's the food calories that we count are actually kilocalories. But when we measure heat transfer in the lab, or when you're doing, I don't know, some other kinds of work, the original calorie unit is just talking about the raising 1 gram of water 1 degree C, and that's the little c calorie. So I don't know. I don't have any good advice there. Try not to get too confused. Just look for the big C versus the little c. In this class, we'll try to keep everything to kcals when we're talking about the big C ones. So you'll only get confused like when you're in lab on Wednesday and we're looking at nutrition labels, they'll have the big C calories. That's what they're talking about. There are some other energy units that we use. Anybody know any other energy units? Joules is another one. Joule is a smaller unit. So there's 4.184 joules in a calorie, a little c calorie. You don't have to know that number. Pretty much any of these conversion type numbers you'll be given. If there's any that you need to remember, I'll tell you very specifically, and they'll be in the objectives list also. So we can convert between joules and calories. There are some other ones that come up here and there, like in household stuff, BTUs, British thermal units, that's another one in the English system. There's, what's another one? Kilowatt hours, which is how your energy use in your house is measured at your meter. But we'll stick to the ones we're going to focus with the lab, which is calories and joules, primarily calories.
What's a capital J, right?
It's a capital J, yeah. The unit is a lowercase j, but the like symbol for it, or the name is a lowercase j, but the symbol is a capital J. So Sorry, I have that right. All right, so one of the things we're going to do on Wednesday, which we can practice now, is calculating the total amount of energy in food based on the quantities of macronutrients. Does anybody know what are the macronutrients that are in food? There's 3 of them, 3 categories. Yeah.
Fat, protein, and carbs.
Yeah, fat, protein, and carbohydrates. Have you heard of those things? They have different energy densities, which means some of them contain more energy per gram than others. Does anybody know what the most energy dense part of your food is? Close. Yeah, it's the fats. And we can find this from the energy density. So fats have 9, whoops, go backwards, 9 kcals of energy for each gram. Okay, so you have 1 gram of fat, which actually wouldn't be exactly that because it's not the same density, but 1 gram of fat stores 9 kcals of energy. Carbohydrates and proteins both give you 4 kcals per gram of energy. Now, from a nutrition standpoint, that doesn't mean they're the same, because your body's going to process things in different ways and use them in different ways. But in just raw, pure energy content, like if you were to burn them, like not burn them for exercise, but like physically burn them, that's the energy that you would get out of them. So if we look at a nutrition label that says, here, this example is a hamburger. Says it has 30 grams or 37 grams of carbohydrates, 19 grams of fat, and 23 grams of protein. We can multiply each of those by the factors written above to figure out the total calories in the food. So we can go 37 grams of carbohydrates times 4 kcals per gram. Grams cancel, and we're left with kcals, which in this case would be 150. No, wait, that's not right. Is it 40? Oh, they must have rounded. Be like, yeah, 148. The fat we're going to multiply by 9 kcals per gram. At 171. And the protein we're also going to do by 4. $92. We could add all those up. And get a total of 411 in that food. And one thing you're going to do on Wednesday is do that for some foods and some nutrition labels and try to figure out or match it up to the calories reported on the label and see if it's the same or not. All right, think you could do that? Questions about that? So again, there's practice in the homework in chapter 3. We sort of talked about this already, but I want to give it its official name. and that is specific heat. Specific heat is the energy it takes to raise 1 gram of a substance 1 degree C. That's like how we define the calorie, right? That's because the specific heat of water is 1, and this is kind of a strange unit, but it's 1 calorie per gram degree C. So it takes 1 calorie to raise water, 1 gram of water, 1 degree C. We can also report that in joules and say that it's 4.18 joules per gram degree C. So that's the specific heat of water. It's a general term though, so specific heat can apply to a whole bunch of different compounds. For instance, aluminum is 0.214 calories per gram degree C. So what does that mean? What would be a way to say that in words? How aluminum reacts to getting more heat versus water? Yeah.
Heats up more easily.
Yeah, so that's might be one way to say it, is that aluminum would heat up more easily. It takes less energy to raise aluminum's temperature than to raise water's temperature. Think about it this way. You're out in summer at the pool, and you got a metal chair, and you got a glass of water. What's going to heat up faster? What's going to be hotter? A glass of water or the chair? The chair, right? You got the same energy coming from the sun, and you actually have less mass of water in there. But the aluminum specific heat means that that energy is going to raise its temperature much, much more quickly. And in fact, water, there's a lot of ways in which water is really special, and this is one of them. Water has a really high specific heat. It's hard to change. It takes more energy to change the temperature of water than most other substances. So that's specific heat. All right, and then the last thing that we're going to talk about in this chapter, and then we can do a little practice if we have time. I don't know if we'll have time tonight. First of all, I guess I should say we're skipping a couple sections in this, so make sure you take a look at that on the objectives, because right after this in the book, they start talking about how to do calculations with specific heat, and we're not going to do that. Same thing with the phase changes we're going to talk about next, melting and stuff like that. We're not doing the calculations associated with that, so you can skip those parts. If you go through the problems that are listed on Blackboard, it skips those problems. So that's why we're skipping those. All right, let's look at phase changes. You probably know most of this already from being alive in the world, but we should at least make sure that we have all the same terms that we're talking about. So I'm going to grab another picture because I think it does a nice job of putting it all together. This is page 76. I don't know if you can read that up there, but I'll tell you what it says. So this is showing water changing between its 3 states, solid, liquid, and gas. And probably you know most of these words, but a couple you may not. So you know that water going from ice to liquid is called melting. Solid to liquid is called melting, yeah? All right, what is liquid to solid called? Freezing, yep. You know this, right? Okay, good. Some people are like, I don't know. Okay, freezing, yep. Also sometimes called fusion, but freezing is good. What is it called when water goes from liquid to gas? Yeah, evaporation or vaporization. And then what about the reverse of that? If you have water vapor that's becoming a liquid, that's condensation. Yep. And so that's shown in these arrows here. I don't know if you can read it from where you're sitting, but it's in the book there. The red and blue has to do with what's happening to the heat. We talked about heat being transferred. So it takes heat to melt something. Heat has to be absorbed to get it to melt. And then heat is released when it freezes. Heat is given off. All right, and then the other words that you may not know, because they're not as common, are when you go directly between solid and gas. So rather than melting, ice can actually turn directly into water vapor. And that is called sublimation. We most commonly experience this with dry ice, because dry ice doesn't melt, it just sublimes. But actually, regular ice does this too. This is why your stuff that you put in the freezer gets dried out. Has anybody ever noticed that? It's because even though that water is solid, it's still subliming and becoming water vapor and leaving. And so eventually that will dry out. And then the opposite of that, going from a solid or a gas directly to a solid without going to a liquid first, is called deposition. And that happens to water as well. That's why you get the like freezer, what do you call it? The frost? The frost. The buildup on the freezer that's like ice. That's because you've got water vapor that's turning directly into ice in the freezer. So those are the different states of water. Make sure you know those words for the different processes. And then what I think is the more interesting part of this is what happens energetically when we go between these phases. So we're going to look at a graph. This also helps us in learning to read graphs better, because sometimes we have issues with that. So here's a special kind of a graph called a heating curve. Let's see if I can get it on here. I'm going to copy it over so we can draw on it. But this is also from your book. And this is a heating curve for water. So what this graph shows is on the y-axis is temperature. So what is the temperature? And then the x-axis is heat absorbed. So remember, temperature is the same as heat, but as heat is absorbed, temperature goes up. So as you add heat to water, what happens to the temperature is what this graph is telling you. For most of the graph, it's pretty straightforward. So let's look at like this regular liquid section right here. If you have some liquid water at like room temperature and you add heat to it, what happens to the temperature of the water? It rises, it goes up, right? You got some water, you add heat to it by putting a burner under it, the temperature goes up. Okay, good. So what's happening then right here? Why is when it starts to boil it, why does the temperature level off? What is that showing? What does that mean? You've got a long straight line, but the temperature is not changing there. Yeah, it's like it's a plateau. Why? What's going on there? What's happening to all that energy?
It's staying constant.
It's not escaping, it's there. The temperature is staying constant. What's happening to the energy? So in other words, if we think about this down at a molecular level, when the water is boiling, a bunch of heat is being absorbed, but the temperature is not going up. So what is all that heat doing?
Oh, it's turning the liquid into a gas.
Yeah, it's turning the liquid into a gas. So it's separating the water molecules from each other. And that takes a tremendous amount of energy. In fact, it takes far more energy to do that than to heat the water up in the first place. Because those water molecules hold onto each other pretty tightly.
So it takes longer for it to boil than it does for it to melt.
For it to heat up or to melt, yeah. Yeah. So I'm trying to grab the numbers here. There it is. So it takes 540 calories to boil a gram of water. How many calories does it take to heat up some water from 0 degrees to 100 degrees? Yeah. To 1 gram of water. How much energy does it take to heat up 1 gram of water 1 degree? Yeah, 1 calorie. So then how much would it take to heat it up 100 degrees, from 0 to 100? 100. So it takes 100 calories to get water from 0 to 100 degrees, and it takes over 5 times that to boil that same amount of water. So that's why, like, when you put water on your stove, has anybody ever done that, like to boil water? Yeah. I'm glad some people have boiled water before, that's good. But yeah, if you turn it on, it gets hot really fast. Like within minutes, you can't stick your hand in there anymore. But it still takes quite a while to actually boil. And that's because it takes a whole lot more energy to separate those water molecules and start that boiling than just to heat it up. So the melting also takes much less. I think it's, I don't want to say the wrong thing. I think it's 80. Yeah, 80. Okay, I was right. So 80 calories per gram to melt. So it actually takes less energy to melt it per gram than to heat it up 100 degrees. So what this is showing us now is if we start way back down at the bottom left-hand corner, here is some ice at minus 40 degrees C. So very, very cold ice. As we add energy, the ice heats up. And then when we hit 0 degrees, we have to add some energy, but the temperature doesn't change. And all that added energy goes to melting the ice, changing the phase. So when you change the phase of a substance, you add energy to do that, but you don't change its temperature. And then you heat the liquid up. When it gets to 100, once again, it's not changing temperature. All that energy is going to boil the water. And then once you put in enough energy to boil all the water, you now have gas, you have water vapor, and now you can start heating the water vapor up, and you could just keep going as high as you wanted to heat that water vapor up. So that's what this graph is showing. What's happening when you add energy and what's happening to the temperature. All right, a couple common things that I see that are problems here. So first of all, it's really important that you remember that boiling does not break chemical bonds. Boiling is not a chemical change, it's a physical change. And this picture shows that really clearly. You've got all these little water molecules, these little H2Os. What happens, well, what happens to them when they go from the liquid to the gas in those pictures? They disperse, they separate from each other. But notice they're still together. Even up in the gas, it's still H2O. It's a really, really common misconception that I see all the time, that when you boil water, you break it up into hydrogen and oxygen. You break chemical bonds. You don't break chemical bonds when you boil something. You just separate the molecules from each other. So that's what we see there. All right. Now another question. This one's a little trickier question and kind of hard to see too. So take a look at the slope, the steepness. Oh, do you have a question?
Yeah, is there a point where you can heat up the gas and not get it starts to separate?
Yes. Yeah. So all bonds have a particular energy, all chemical bonds have a particular energy to them. And if you give it enough energy, it will break that. The easiest way to do that with water is called electrolysis. You can pass an electric current through water, and if the current is high enough, you can break that up and form hydrogen gas and oxygen gas. Yeah. But yeah, thanks. So take a look at the slope of the liquid and the gas, the steepness of those lines. You'll notice the liquid is kind of a shallower and the gas is kind of steeper. What does that mean? What does the steepness of that line tell us?
How quickly the change happens?
Yeah, so what is that? What controls that?
The heat absorbed.
Kind of. It's how the temperature reacts to the heat absorbed. We had a name for that a little while ago.
Specific heat.
Yeah, that's specific heat. So the specific heat tells us how quickly does the material change temperature for a given amount of energy. And so what can you say about the specific heat difference between the liquid and the gas? Which one has the higher specific heat? Liquid water or gas water vapor? Liquid? Why? You're right, yeah.
It takes longer for it to come to the boiling point. Whereas
Yeah.
for it to change from a solid to a liquid, and then liquid to gas.
Yeah, so, yeah, right. So if you look at the steepness of those curves, we can say it takes longer, it takes more energy to raise the temperature of the liquid, whereas the temperature of the gas shoots up more quickly. And so that's showing us that the specific heat of the liquid is much higher. And we know the specific heat of the liquid is 1 calorie per gram degree C. The specific heat of the gas is a little bit lower than that. That's where those slopes come in. So this heating curve tells us all that stuff. It tells us about relative specific heats. It tells us about boiling points. It tells us about amount of energy that it takes to boil, all kinds of stuff. So what are some things that you should be able to do dealing with changes of states? Let me show you one example. This is on page 89 in the book. Okay, here's an unmarked heating curve. It has some labels on it. This is for chloroform, a solvent, organic solvent. So just a blank heating curve for chloroform. What is the approximate melting point of chloroform? Careful. Yeah, negative 60 degrees Celsius. Did everybody see that? You're assuming that you're starting in a solid, heating up the solid, and then melting it. So where it's melting is right here, this B section, and that looks like just below minus 60 degrees C. All right. So what's the approximate boiling point of chloroform? Yeah, so that's going to be up here at like 60. Where does the other phase change? Which phase of chloroform has the lowest specific heat? This is a tricky one. Which phase of chloroform has the lowest specific heat?
Yeah.
Gas? E? Yeah, it's kind of hard to see. I think it could be.
Could be gas or liquid.
Yeah.
I think C is the steepest to me. No? Yeah?
Hard to tell.
It is hard to tell. I shouldn't ask that question. But whatever one is the steepest has the lowest specific heat because it means that it goes up in temperature the fastest with a given amount of energy. So that, yeah, it looks to me like C, but it could be E. A definitely looks shallower to me, but I don't know about E. All right. At the following temperatures, this is what the book asks, is chloroform a solid, liquid, or gas? So at minus 40 degrees C, what is the state of chloroform? At minus 40 degrees C on this graph. It's a liquid, right? So if you saw a question like this, like on the quiz or exam, one thing you might want to do is just start labeling it because it always goes in order, right? You're going to have solid, liquid, and gas. And that means that you're going to have melting here. And you're going to have boiling here. So then you can use that and say, okay, minus 40, that's about here, in between minus 60 and minus 20. So that's a liquid. On Wednesday, you're going to construct part of a heating curve for water. So you're going to construct kind of the C and D parts by taking liquid water and boiling it and measuring the temperature as you're adding energy and kind of seeing what happens. And you may see some slightly unexpected things there, but we'll talk about how to explain those when we get to that. All right, so that was a lot. Yeah, good job hanging in there. I'll try to make other Mondays less boring, but we're just trying to catch up a little bit because I know we're missing next Monday. Normally there will be some more time for like working on practice problems and things like that, but that takes us through chapter 3. So make sure you're working on the homework for chapter 2 and 3. And come see me if you have questions. Come to lab with questions on Wednesday. Even though lab is lab, there's usually some time to ask questions just because we're waiting for stuff to boil or whatever. In terms of lab stuff that's due, so on Wednesday, make sure that you bring your lab from last week, the packet or whatever, the parts that you had to write on in the packet. So that would be the answering the questions, doing the measurements, that kind of stuff. Make sure that you've completed the pre-lab for Wednesday's lab before you come in. So that will be the energy and matter lab, but you'll tear out the pre-lab, complete it, and turn it in before we start on Wednesday. And then that's all that's due. And then there's going to be a practice quiz on Wednesday too. You don't have to do that for this lab. Some labs, I think actually starting on Wednesday, some of the labs have an electronic component where you type in your data so that everybody can see everybody else's data, and you'll do that to like answer some of the questions. So when that's a thing, that's just something you do like during the lab. You'll just type in your data as you do it. Yeah. Any other questions about stuff? Yeah. Go ahead.
So the practice quiz is on what?
Wednesday.
And like on baseline will be.
What we did today, kind of. So it's not ideal because we only have 2 days until we do it, but it'll be the same material that's on next week's quiz, which is the stuff that we're doing that we did today and last week. So chapter 2 and 3.
So this one was it.
So practice quiz Wednesday and real quiz the week after. Other questions?
Can I just ask?
Yeah, sure.
So I know you were talking about the rounding off and
Yeah.
it not being a big deal, but I just got a little confused. So like this number,
Right.
all of the zeros are significant. So that means that
No, they're not.
no, they're not.
Zeros that are between a decimal place and a number are not significant. Zeros at the end are.
Okay.
At the end of the number are.
So then if it's asking me to round it to 3 significant figures,
Mhm.
it would just be 473.
It's 474.
474
round
because
up
you'd
from
round
the
the
eight.
last one.
Yep.
Okay. And then there's another one. Here. It's the same thing, right?
Yep.
Okay.
So that
So that
zero
was
is
where I kept
significant.
getting caught up. Yes,
Yep.
I start all of those. Okay.
Yep.
So it's always after, or can you say it one more time? I'm sorry.
So zeros after the numbers after the decimal places are significant.
But prior to them are not.
Right.
Okay.
And the maybe it's helpful, like the reason for that or where that comes from
Uh-huh.
is zeros before the decimal place are a measure of magnitude. Like how big is the number? Is it really small or is
Okay.
it really big? But it's not part of the measurement itself.
Okay.
Same
Okay.
thing like this. Like if you see this number,
Uh-huh.
those zeros are not significant because this is just telling you it's a really big number,
Okay.
but that's not part of the measurement.
So
If
did I
it's not a
write it right in
decimal
the
place.
scientific notation then?
No, that should have been
Just 51?
5.1.
5.1?
So you
But
just have two
times to the
significant
zeros,
figures.
no or no?
Yeah, I don't know. What number do you have here for number zeros?
4, because I was counting, I was making a 5.10 and then going past to the zeros, because I was thinking the zero was significant.
No, so it should be
no.
5.11 to the that would be 366.
Okay.
Yeah.
Okay. Okay.
Yep.
And then you were saying for the conversions, you will always give us the conversion, so we don't have to learn them.
Except for those 3 prefixes.
But like from this one, I got really caught up on the odometer 2250.
2250.
This is kilometers, right?
Right.
And you wanted me to do it in miles per hour.
Miles, yeah. Not per hour, it would just be miles.
Miles, right? But then that conversion would be one that you would provide for us.
Right.
Okay.
Yep.
Okay.
Yeah, anything going between systems or anything other than the kilo, centi, and milli,
Okay.
you have to be provided.
And then like this one being, this is the bigger M, so
Mega, yeah.
mega. So,
So
how
you
would
have to
that?
know that one,
I don't have to know that either.
right?
I don't. Just
But
the
it's a million.
kilo, centi, and milli.
Right.
Okay. All right. Okay. Thank you.
Yeah. So while